Go. All right. So I just have 2.5 pages of notes to get through, and then this course is over. Okay. What? Yeah.
I'm not on. I can talk all I want.
Oh, that's right, you can.
I can talk all I want.
Don't bite your tongue.
Oh,
No.
crap. I've done that talking before.
Well, this means you have to talk more, not by your tongue. Okay.
Huh?
So whatever you bite your tongue about, just let it out. Then you won't hurt yourself.
Right. I just to not let you know they're gonna hurt.
Yeah.
Oh,
Okay.
man. This is like some Cold War tactic or something.
Okay. So we're still dealing with fixed points, and whether they're stable or not. All right. So there's 2 categories that we could break down to. So if the fixed point is hyperbolic, well, that's the case we've been talking about. So in that case, you can use a linearization theorem and say, oh, your system is topologically equivalent. So you can study the fixed points of a linear system. And you can easily determine whether the fixed points of a linear system are stable or not. And that tells you what's going on with nonlinear systems. So that's what we've been dealing with prior to this point. If the fixed point is not hyperbolic, and just to refresh your memory, what I mean by that is either the determinant of your Jacobian matrix is 0, or the eigenvalues are purely imaginary. Then that's what we're going to look at today, using what are called Lyapunov functions. I think it's the correct pronunciation. I'm not entirely sure. Actually, I've often seen Lyapunov spelled with a Y, L-Y-A-P. This is the first time I've actually seen it with an I. Okay, so all I'm going to do today is I have first I've got to explain what are Lyapunov functions and how we use them to study stability of non-hyperbolic fixed points, and then I have a couple examples, and then we are done. I can go pick up my cat. Okay.
It should encourage you to fly through this.
Yes, because besides they close at 6. That's right. You guys have a. Also, I have to end before 4:45, right? You have your 2-hour analysis class today.
We're getting our final exam.
Oh, right, for the take home. Yeah. Fun stuff.
It's like Dr. Lambert attends that class. He knows everything.
Actually, that's true of a lot of classes. Okay. So, first definition, we need to define the Lyapunov function. It's called the covariant derivative. Okay. So, a covariant derivative of a function f, which is scalar value. So maps Rn into just for real numbers. And you take a covariant derivative of a function along a vector field, big X, just like any of our other vector fields. So the notation used for a covariant derivative is it's a gradient of f, but you, for covariant derivative, you take the vector field as a subscript. And the way you define it, it's actually similar to, actually it's almost exactly the same as directional derivative that you may have seen, well, you should have seen in multivariable calculus. So it is just a plain old gradient of big F, but then you take the dot product with your vector field big X. So to compare, when you see multivariable calculus, the directional derivative is similar notation. I usually capital D, and then a subscript U is your direction of F. Is a gradient of F, dot product with U. So it's, both cases is a gradient and dot product. The difference is directional derivative, the direction is taken to be a constant vector. In fact, it has to be a unit vector. Whereas here you're taking a directional derivative, except your direction is not constant. It's a function of x. And it doesn't have a requirement that it has to have unit length, which I think would have been a good idea, but they don't put that requirement in here. Okay. So, in other words, I guess the way to, and I can write this out in terms of partial derivatives. So, partial derivative of f with respect to xj at x times the jth components of the vector field big X. But that's this definition of dot product that's giving us that.
What
yeah.
is the 2 for?
Oh, shoot. Vector 2 norm, Euclidean length. So that subscript is often used because there are many ways to measure the magnitude of a vector, but the subscript 2 means Euclidean length square root of some squares. And I forgot I was bringing numerical linear algebra notation into a DE class. Okay. In fact, often when a norm like this is given and there's no indication of what it is, for a vector, chances are it's still Euclidean length. Okay. So as far as a interpretation of this covariant derivative, because you know that the derivative is a rate of change. So it is the okay, clearing your throat doesn't count. It's a rate of change of f along the flow lines of big X. But if you think about when you're plotting a vector field, let's think of like a phase portrait, you're plotting a vector field X, you're seeing throughout your domain which direction is big X going in. So now you're looking at, well, at what rate is the function changing along those directions? As opposed to here, you're caring about how f changes along certain coordinate directions. But now this is a direction you're caring about. Okay. All right. So that's a covariant derivative. And now I can use this definition to define the Lyapunov function.
I feel like every time you look at the computer screen, you freak out that it might stop recording.
Yes, I do. Fortunately, nothing much has been lost. Okay, and actually, I used to have both my classes next semester that are back-to-back in this room, so I could take both classes, 561 and 606. But it'll still be two separate videos. So. Okay. So next definition Lyapunov function. Okay. A Lyapunov function for a fixed point C of some vector field X. So big X of C is the 0 vector. Is a C1 function, and I've used this notation before, C1 means it's continuously differentiable. And the notation used for the Lyapunov function is this big lambda here. And it has to have these properties in order to be called a Lyapunov function. So first, the fixed point has to be a local minimum of the Lyapunov function. So there has to be some neighborhood of your fixed point, such that on that neighborhood, if you look at points near C, but not equal to C, so more intuitively, C is a local min. I should say a strict local minimum, because it has to be strictly less than. Okay. So that's one criterion. And then the second criterion is that the covariant derivative of lambda has to be non-positive. Again, for x near C and not equal to C. So those are conditions for a Lyapunov function. We can go a little bit further. Like, let's suppose that this inequality here, what if it's strictly less than 0? Then that means we say that big lambda is a strict Lyapunov function. Okay.
I know I'm not the only. Okay, I started to die out laughing. When you drew the little lambda, it looks like some little character with like little feet or something. I know I'm not the only one who saw that. Anybody else? Like in Alice in Wonderland, the little cartoon version of little cards that have the little feet like
Oh
that.
yeah, okay.
Am I the only one that saw that?
I saw a wizard hat.
Oh, okay, well it's a little character design something, and I just started dying out laughing. And no one else did. And I'm like, all right, I'm a goofball, but it's okay.
Well,
That's the only, and I had to look up the actual lambda to see what it really looked like.
yeah. Yeah. Okay. So in other words,
That's just how you write it.
big lambda has to be a character of some sort. So it's a wizard hat or a little.
Oh, look at feet.
Yeah. Okay.
They remind me of feet. Or like when a kid draws stick figures, feet. I'm sorry.
Okay.
I had to get that out.
Alrighty. Okay, so those are conditions. Now, what does this condition, the second condition, actually mean? So for this, we have to look at what is the meaning, geometric meaning of a dot product. So we look at a dot product. Now, the way you normally compute it is u dot v is you multiply corresponding components and add them up. But there's another formula for a dot product that physics majors like to use that actually is going to be more intuitive for us. They don't have to know what is the other formula for a dot product.
All you do is add, wait, okay, hold on. You add up. Just give me a second, because I feel like I should know this.
You're dying to answer, are you?
He can't answer though. He's got to keep quiet.
Nice
Oh,
job.
it's got the IKJ stuff, isn't it?
No.
No? That's how we did dot product though.
All right, I'll let you answer.
No, wait, no, because then you're going to catch us on it and cheat. Is that cheating if you let him answer this one?
No, it's
Okay,
explicitly
all right.
allowed.
Doesn't it have to do with like norms and
Yes.
Oh, yeah.
something norms and
Some-
cosine and
Yes, cosine.
Yeah.
Okay, you're right.
Huh, we got it without you.
No.
We got it without you. We got it without
No,
you.
no.
Don't say anything.
Write it down.
Don't
Write
say
it down. Down.
I'm keeping like as still as possible so that like my knee doesn't pop funny. So you have to be quiet.
I got it. Norman cosine. That's what I said.
Yeah.
Go Haley.
Where theta is the angle between u and v. So what does it mean when the so the dot product is equal to 0 versus the dot product being negative? So geometrically, this is cosine of the angle. So here cosine is 0. Here cosine is negative. So what can be said about the vectors u and v in this case? Or dot product?
They're
Orthogonal.
I was gonna
Yes.
say perpendicular, but that's the same thing.
Yeah. Okay, so u is perpendicular to v, so in a situation like this. Okay, and what if you're negative? When is cosine negative?
When it's on that side of the unit circle. Wait, I gotta think about it first.
Yeah, and
When
for those of you who couldn't see, Abdullah's doing
I
this.
said when it's on that side of the unit circle.
Grades.
It's when it's
I just keep going to the next
The
one.
side
That's hilarious.
it's values of pi. It's like when you say cosine of pi, that's -1. So
Yeah.
those
Yeah. So
those things.
yeah, so the angle is obtuse.
So they're
Yes,
in
I like
opposite direction.
Yeah.
Yeah, I was on the right side.
By the way, if you haven't seen it, you need to see an episode of Family Guy where they do the
Make me.
where
I don't have to.
they do a parody of a Shawshank Redemption.
Oh yeah.
And they
Yeah.
have a obtuse and acute. Yeah. So, and if you haven't seen it, you can find just that clip on YouTube. So it's definitely something any math person would appreciate. Okay. So all right. So that's what happens in this case. So what does that mean for a
Hey, when you drew that top one right there, were you trying to show that it was acute, or were you just trying to show that they were angles with
oh, just
an angle?
here's the
Okay.
angle. Yeah.
Just checking.
At least now we have all the situations. Yeah. So in this
You don't
case,
have the acute situation. That would just be greater than 0.
yes.
Yeah. Okay.
All right. So what does it mean in this case where you also have C being a local minimum? Because the other thing is the gradient of f, so without any dot product, it's a regular derivative. That is the direction of steepest ascent.
Oops.
Minus gradient of f is direction of steepest descent. Okay, so that's the direction in which f is increasing the most rapidly. So now let's take all these concepts and put them together to see what is going on with this covariant derivative of a Lyapunov function having to be either 0 or negative. Okay. Oh, I need to fix this first. And why this should tell us anything about a fixed point being stable? Because for a fixed point to be stable, that means we want it to attract nearby integral curves towards a fixed point. Okay.
Given enough time, we'll get the answers. Just takes us about 3 minutes longer.
Hello. You said hello.
Oh.
Is it me you're looking for?
All right.
More.
So if a gradient, so if you look at the covariant
It's upside down.
derivative of lambda
I can show it to
being
you after class.
equal to 0. So what this is saying is the gradient of lambda is perpendicular to big X, where X is near C. All right. Now, so what that means is that gradient of lambda coincides with a, okay, so orthogonal, no, big X coincides with a level curve of big lambda. In other words, big lambda equals constant. If you have any function of several variables, you can have like what's called a level curve or level surface or level set, where a function is constant. Think of it like if you have a function representing altitude, and you have a contour map showing where a certain altitude is assumed. Those contours are your level curves. So if you like, you can think of it that way as contours, and certainly two functions of two variables. Okay. So what's happening is, here's your fixed point C. That is a strict local minimum of big lambda. So here's some level curves. And you can think of this being in some sort of valley, and C, your fixed point, is at the bottom of this valley. Okay. So this situation, here's your direction of steepest increase. So this is a gradient of big lambda. But then, here is big X. So this is for a case where the covariant derivative of lambda equals 0. All right. So what this suggests is that the solution curve, which is traveling in this direction, is tending to orbit around the fixed point. So C is acting like a possible center. Because what's happening is the solution curve, which is traveling in the direction of big X, wants to orbit around C. Because what is stability? Oh, I should say instability. Instability is when the solution curve wants nothing to do with C. It is shunning C and running away from it. Well, if it's running away from C, then it should be going more in this direction, in the direction of a gradient of big lambda, steepest increase. But no, it's orthogonal to that. Now, let's draw another situation where here's your gradient of, I can never draw red symbols, a gradient of big lambda, steepest increase, and now we have a covariant derivative being negative, so big X is somewhere over here. So this is happening in a situation where the covariant derivative of lambda is strictly less than 0. So big X is doing the opposite of running away from C. It's going towards C. So in this case, all right, so covariant derivative being negative means that solution curves tend to approach C. Okay. All right. So either way, you have some notion of stability. Now, if you have C being a possible center, so you're getting curves that are orbiting around C, but they're not necessarily drawn to it, this is just plain old stability. However, if you have integral curves being all drawn towards C, instead of orbiting around it, That is asymptotic stability. Okay.
This might be a dumb question,
Uh-huh.
but normally you write like the gradient symbol and then the little vector like subscript
Yeah.
after the gradient.
Uh.
Right at the bottom where you put solution curve tends to approach state,
Yeah.
you write the gradient and then the lambda and then the subscript. Does that matter?
I wrote it wrong.
Oh, okay.
Yeah. Gradient followed by what you're taking gradient along,
Okay.
then when you're taking the gradient of.
Okay. I just wrote all of it.
Yeah, I seem to have trouble keeping my symbol straight today, more than usual.
I was just checking.
Okay.
It's because they all look the same. They're
Yeah.
all just like that, just turned different ways.
Yeah, I think that's kind of throwing me
They're all
off too.
triangly.
Okay. All right. So the thing is, what this means is if we can find some function that has this property where c is a strict local minimum of it, and then the gradient of this function is behaving in this manner with respect to a vector field x, that the gradient of this function is going one way and the vector field is going the opposite direction, literally. So it is meaning, and because it's a local minimum, that's how the gradient of this function is going to behave. That you're going to have because it's strict local minimum, any increase is going to be away from it. So if we can find a function that has these properties, that tells us that the fixed point is going to be either stable or asymptotically stable. So, so that leads us to the one and only theorem of this section, where we can figure out stability for non-hyperbolic fixed points, where you're not able to compare a linear system. Okay. And just to make it easier on all of us, I'm not going to bother proving these, but I've already given at least the intuition for them. And the fact is, there are a lot of cases where you can see a proof of a theorem, even understand a proof, and it gives you no intuition whatsoever as to why the theorem is correct. Which is kind of unfortunate because I think it's kind of counterproductive in a way. That's just me. Okay. So our theorem, it's called the Lyapunov stability theorem. So C is a fixed point. It could be hyperbolic or not, but we're only going to think of non-hyperbolic really because if it was hyperbolic, we could do something else that's simpler. So C is a fixed point of x. So if there exists a Lyapunov function, big lambda, for this fixed point. So in other words, it's a strict local minimum of lambda, and the covariant derivative behaves in the right way. So if we can find such a function at all, and C is stable. Now this theorem does not give us any guidance whatsoever on how to find this Lyapunov function. It says, but if we can find one, stability is established. And so that's one condition. Second condition is if there exists a strict Lyapunov function for C, and C is asymptotically stable. Because that's the case where all the integral curves are running towards C. Whereas in the first case, they may be orbiting around C, so you have a possible center. So that's it. If you have a system where you have a fixed point and you find it's not hyperbolic, then you can try finding a Lyapunov function. And good luck. Don't worry, I'm not giving a problem where you're supposed to find one. The only problem I gave in this section is where you have a given candidate for a Lyapunov function and you can check the conditions to see if it really is or not.
I'm not going to jinx it, but I had a nice remark to that.
Me too.
What?
Nothing.
Nothing.
Just going to hold out for how many more pages of notes you got?
Right. Okay. Well, yeah, you hope to not even have to do this problem.
You said it. not us.
Or should I sweeten the pot and say that you can
No diabetes.
We can what? Choose not to do any of the.
any one?
six?
Yeah.
Any one of
That's
them.
a
Yeah,
good deal.
Because if you find chapter 6 easier than, say, number 5, then. And you might feel that way because 6 has not many problems.
What's the catch?
But don't get
Yeah, I was gonna.
No.
Really?
not this time. And you guys are already under a bet. And
Are we doing our times?
okay, we have about half hour left.
Mm-hmm.
Okay, but all I have left now is okay. I've already given an intuition behind this theorem being true. I just have these 2 examples to get through, and that's it. Okay, so using this one theorem. Okay, so here's our vector field in 3 dimensions. I think this vector field has come up in other examples. Yeah, it has. Okay, so here's a vector field, and we now there's actually several fixed points, but we don't care about just any old fixed point. We care about ones that are not hyperbolic. So one fixed point that we'll take a look at is just the origin. 0, 0, 0. Okay.
Are those? Is that like little y, little letters on your example?
Yes.
Okay.
Is that a Z or a 2?
Oh, that's a 2. I put a little line through it to distinguish a Z from a 2. After many complaints from students. Okay. Now, so what you do is to check whether a fixed point is hyperbolic or not, you have to compute a Jacobian. So the Jacobian, so x prime, evaluated at 0, 0, 0. So you compute the partial derivatives of these with respect to x, y, and z, get a 3 by 3 matrix. It's written in notes, I won't write it out here because I want to get out of here too. But if you plug in x, y, z equals 0, 0, 0, what you get is this, mostly 0 matrix. Okay. And because it has a row and column of zeros, this is not invertible. So anytime you have that, so it's the fixed point is not hyperbolic. Okay. So the consequence of that is you cannot use the linearization theorem to judge the stability of this fixed point. There are other fixed points you can see. For example, if you set z equal 1, x and y equals 0, but you would find that fixed point to be hyperbolic, so you can just use the linearization theorem for that. So we're not looking at cases like that. Okay. So we need a Lyapunov function. So all I'm going to do here is, we're not going to go to trouble of trying to find it. We actually have a Lyapunov function that we can use. So I'm going to show that it really is a Lyapunov function. Okay, so our proposed Lyapunov function is 1/2 x squared plus y squared plus c squared. Although I have to confess, I'm not really sure why we care about the 1/2, or what it's doing there, but whatever. Okay, now this is actually a good starting point for a Lyapunov function for any system, where at least if your fixed point is the origin, you can have x squared plus y squared plus z squared, or if it's not the origin, you can have like x minus x naught squared plus y minus y naught squared plus z minus z naught squared. The reason why this is a good starting point to find any Lyapunov function is because this actually does have a strict local minimum at the origin. So, and the reason why is because the gradient of lambda is x, y, z, and this equals 0 only at 0, 0, 0, because that's a critical point to find the minimum. And then the Hessian of lambda is the matrix of second partial derivatives. Well, if a gradient is x, y, z, the Hessian is just going to be the identity matrix. The identity matrix is positive definite. Throughout R3. So when you have a Hessian matrix that is known to be symmetric positive definite, not just at the critical point, but throughout the whole space, then that tells you that your critical point, 0, 0, 0, is a strict local minimum. So right away that satisfies the first condition for a Lyapunov function. So I can give you a general guideline if you need to find a Lyapunov function and you're just not sure where to start. And I'll just write it down for 3 dimensions. You can have x minus x naught squared plus b, y minus y naught squared plus c minus z naught squared, where x naught, y naught, z naught is your fixed point that you're studying. And the constants, a, b, and c, all have to be positive. So any function of that form will automatically satisfy the first condition for a Lyapunov function. It has a strict local min. In fact, it's a global min at your fixed point. Okay, so what you could do is you can try the simplest choice, like we have here, all the coefficients being the same. See if that works, see if it satisfies the other condition. And if it doesn't, then maybe you could try adjusting A, B, and C so that it does. Okay, so, all right, so at least you're not totally left adrift, because you have to find functions that are going to have a strict local minimum at a certain point. This is the simplest kind that has these sum of squares here. Okay. Now, okay. So now we got to check the second condition. We have to look at the covariant derivative of this Lyapunov function and see if it can be guaranteed to be at least non-positive. All right, so we'll just go ahead and compute that. So the covariant derivative, I'll write in the correct order this time. So that is a gradient of lambda of x, y, z, dot product with your vector field, functions x, y, z. Well, your gradient, I computed that earlier, that's just x, y, z itself. And I take a dot product with your vector field, which is, okay, so y times z minus 1, x times z plus 1, and then minus 2xy. All right, so we just go ahead and carry out the dot product. So we get x, y, z minus 1, 2. Just multiplying corresponding components and adding them up. And then have minus 2x, y, z. So we go ahead and expand this. So we have x, y, z minus x, y plus x, y, z minus xy minus 2x, y, z. And what happens to that? Whoops, I made a mistake. Plus.
Shut up.
I'm gonna kill him.
Look at this inner struggle over here.
They cancel out. You get 0.
Yes.
Get 0.
Rosie.
He looks
I
like
just
he's
love
gonna
the
cry.
struggle. The entire class, it cracks me up.
Okay, let's try not to have a number slip up between now and the end. Okay, so it equals 0. So that means that lambda is a non-strict Lyapunov function. Would have been strict if the derivative had been negative. So that means that your fixed point, 0, 0, 0, is stable. Not asymptotically stable, but stable. So in other words, it's acting like a possible center that we're getting nearby solution curves tending to orbit around it. Okay. All right. So that's that example. Questions about that example? All right. I have one more. This is a two-dimensional system, both a somewhat nastier vector field. So big X of xy is minus y plus xy minus x cubed minus 1/2 xy squared. That's the x component, and the y component is minus 3y plus xy plus x squared y minus 1/2 xy squared. Okay, now it'd be kind of a pain to find all the fixed points of this.
So you're just gonna tell us.
Yes, I am. So let's look at 0, 0. Is a fixed point. And what happens is, and there's details in the notes, but if you were to compute for Jacobian matrices that take derivatives of both with respect to x and y, partial derivatives, and then plug in 0, 0, you get this matrix. 0, minus 1, 0, minus 3. Details are in the notes. So this, again, this is not invertible. So this is not a hyperbolic fixed point, so we cannot use the linearization theorem. We need a Lyapunov function. Okay. Now, we could have tried similar functions in the last example. 1/2 x squared plus y squared, because that would automatically satisfy the first condition that has a strict local minimum at 0, 0. However, okay. So the trouble is this does not satisfy the condition, second condition. So it does not work because this fixed point is actually a saddle point. Of the covariant derivatives. What happens is there's increase along some directions and decrease along others. Okay. All right. Now. Yes, I do. Okay. So it's something we can try, but it's not going to pan out. So we're going to look at a different function that actually is not of a form that I had over there, necessarily, but it turns out to work out, and we can verify those conditions. Okay, so instead, look at this candidate for Lyapunov function is 1/2 3x squared minus 2xy plus y squared. Okay. Now, one thing that can be done is this can be rewritten as 2x squared plus x squared minus 2xy plus y squared. And now that last part over here, that's a perfect square. So I can write it in factored form. So we just have x squared plus 1/2 x minus y quantity squared. So because it is a sum of squares, like this, it actually has a strict local min. So at wherever the sum of squares, the individual terms being squared are equal to 0. So here we must have x equal y because of this condition. But because of this, x squared, we must have x equals 0. So that means that x, y being 0, 0 is a strict local min. Actually, I can say more than that. It is a strict global min. So anytime you have something that's a sum of squares, you find out where all the terms being squared equals 0. That is your strict global min. So first condition is satisfied. And your fixed point is a strict global min of this proposed Lyapunov function. Okay. So it took a little more work to see that than for just x squared plus y squared, but it still works. Okay, so now we got to check the second condition. So the covariant derivative of lambda. So that's going to be the gradient of lambda dot product with big X. Now the gradient is going to be, well, if you take the gradient of this, you take a derivative of this with respect to x, and you get 6x minus 2y. And then this derivative with respect to y is going to be minus 2x plus 2y. So that is the gradient of lambda. And then you take a dot product of that with the vector field that I have written over there. So that's going to be all this mess. Okay. So now you have a rather messy dot product to work out, and I'm going to spare the algebraic details here, because I know you guys can all handle that. We'll send the notes anyway. But once you simplify this as much as you can, you actually can recognize a difference of a perfect square again, like this one. In fact, it's exactly that one. You get, or no, it's not the same, but it's still a perfect square. So it's minus x squared minus y squared minus 2x to the fourth minus y squared. Okay. So notice all these are terms raised to an even power, but they're negative. So, and the only time it's going to be equal to 0 is at the origin, at 0, 0. But we don't care about that point. We're looking at points near the fixed point. So this is going to be strictly negative for xy not equal to 0, 0. So now it meets the second condition for a Lyapunov function. In fact, because it's strictly less than 0, we find that lambda is a strict Lyapunov function. So that means that 0, 0 is asymptotically stable. In other words, it draws all nearby integral curves towards it as opposed to acting like a center. All right, so no orbiting, it's just a black hole, it sucks them all in. Okay. So that's how you check. You see, and in this case, the Lyapunov function is a nice enough form where you can factor it and recognize it as sum of squares. If you can't do that, and this is actually what I did in notes, you check if the Hessian is positive definite. Using kind of test similar to what you do in multivariable calc. So that's something you can do for more generally about a function. But what's written is something you can write as sum of squares. That's a lot easier way to check for your fixed point being a strict global min. Okay. Now, to wrap up this example, so earlier I suggested what about the Lyapunov function 1/2 x squared plus y squared. That would have satisfied this condition still, but it would not have satisfied this one. So let's take a look at that and see where it would have gone wrong, just so you can tell. And then that'll be it. Okay. Oh, and it's getting close to time to wrap up anyway. All right. So okay, so we look at the covariant derivative of this function. So a gradient is going to be, well, partial with respect to x is just x. And partial with respect to y is just y. Dot product with your whole vector field. So minus y plus xy minus x cubed minus 1/2 x y squared. And then you have minus 3y plus xy plus x squared y minus 1/2 xy squared. So then you go ahead and carry out the dot product. So that's going to be minus xy plus x squared y minus x to the fourth minus 1/2 x squared y squared. So x times all this plus y times all this. So minus 3y squared plus xy squared plus x squared y squared minus 1/2 xy cubed. So then we have to see about any like terms. Well, we don't have much actually. So for instance, these two terms combine, so we have 1 plus 1/2 x squared y squared. Yeah, that's pretty miserable actually. Now the thing is, all we have to do is find one point, one xy value at which this can be positive, and then it's done for. So now to make things a little easier, let's set x equals 0 to wipe out most things. So then we get minus 3y squared. And you set y equals 0, so we get minus x to the fourth. Okay, so that, okay, at least those are negative, so that does not entirely help. If you set x equal to y, so that'd be, we could definitely combine more terms there. So minus x squared plus x cubed minus x to the fourth minus 3x squared plus x cubed plus 1/2 x to the fourth minus 1/2 x to the fourth. So those last two terms cancel. And we have 2x cubed minus 4x squared. Okay, so you have,
Wait, where'd you get that x to the fourth?
that one.
I don't know, but where'd you get that one? You combined the terms of, what terms did you combine?
Well, I had, this came from,
No, go up, yeah,
What?
go to the right.
Yep.
That x to the, no, not that far, not that far. The x to the fourth, two terms over. That one, yeah, no, go to
The one right. She's talking about the negative x.
the negative x to the fourth.
yeah,
No,
No, the one on the equation.
yeah, where did that come from?
x times that.
Oh, you're multiplying that.
Yeah,
Never mind. I was
yeah,
just
x times first component plus y
Right,
times second
right.
component.
I guess I didn't realize that was a multi. Never mind.
Okay,
Don't listen to me.
now,
Oh.
if, in this case, let's see, so because we have a mix of positive and negative terms here, well, actually, I can factor out an x squared. So you get minus 4 plus 2x minus x squared. That part's always going to be positive. This is a quadratic that's opening down. Okay, so when x is 0, it's good. Oh, that's always going to be negative. Well, this sucks. I mean, all it takes is one direction for it not to work out, and that's all you would need. Because a more conclusive way to do this is to, if you take this function and see like where its maximum is, if it has a maximum, and the maximum should be non-positive. So if I take the gradient of the covariant derivative, so that would be derivative of all this with respect to x. And then the other component being with respect to y. And you'd have minus x plus x squared minus 6y plus 2xy plus x squared y minus 3/2 xy squared. So that's your gradient. And if you plug in xy equals 0, 0, that would definitely be a critical point. But then you'd have to look at the Hessian of this. So then we're looking at second derivatives, first with respect to x, and you'd have 2y minus 12x squared plus y squared. And then over here you'd have same thing with respect to y. So you have minus 1 plus 2x plus 2y plus 2xy minus 3 halves y squared. And notice if you plug in 0, 0, you're going to get a minus 1 here. And that same entry goes down here. It's symmetric, so I'm not going to compute it. And then this with respect to y is going to be minus 6 plus 2 plus 2x plus x squared minus 3xy. So then, if you plug in at 0, 0, so what you get for the Hessian is 0, minus 1, and then minus 6. And to see how that behaves, is it a local max? Is it a local min? Is it saddle point? You look at, you go ahead and compute the eigenvalues of this. But the trace is minus 6, and the determinant is minus 1. So, okay, so if okay, so that means that the eigenvalues are opposite sign, except they're actually going to be complex. No, that can't be right because it's symmetric. The eigenvalues have to be real. If they have opposite sign, well, the trace is minus 6. So lambda 1 plus lambda 2 is minus 6. Lambda 1 times lambda 2 is equal to minus 1. Okay, so the eigenvalues are equal to minus 3 plus or minus the square root of 36 minus 4 times, okay, plus or minus the square root of 40. So, okay. That doesn't look right.
I didn't need to divide a 3 by the 2.
Actually, it's the trace over 2.
Oh, okay.
Yeah.
Never mind. Keep
Okay, so 36 plus 40. Oh, square root of 10. Okay. Yeah, so that gives you an eigenvalue that is 1 positive and 1 negative, because square root of 10 is roughly 3.16. So the conclusion is 0, 0 is a saddle point. And I mentioned that earlier, but I wanted to prove it. Of this lambda. Well, we can't have that happen. That near C, so what you have is it could be increasing in some directions and decreasing in others. And that's why it's not a suitable candidate for a Lyapunov function. Okay, because what's happening is this covariant derivative. If you plug in xy equals 0, 0, you're going to get that the covariant derivative is equal to 0. And what's happening is the covariant derivative from 0, 0, because of what I've shown you here, is going to be increasing in some directions and decreasing in others. That means that along a direction where it's increasing, that means that the covariant derivative is going to be positive for some xy near 0, 0. So that's what you can do. So if you're not sure if a function is a Lyapunov function, or a suitable candidate, to see why it would fail, take your covariant derivative and check out the behavior at the fixed point. is because if a covariant derivative is equal to 0 at your fixed point, that means you have to make sure that from a point you've lost a chance. Well, it could still be a strict Lyapunov function, but you have to make sure that there is only decrease away from that point. So if you find that, okay, so running out of time, aren't I? I'm maybe I'm already out of time.
Yeah.
Oh God, I'm late. Sorry. Okay, so I'll just write down the bottom line, and that's it. So I need to turn this. Okay. So if the fixed point C satisfies that the covariant derivative of lambda at C equals 0, then C must be a local max of this covariant derivative. Okay. Otherwise, it is not a Lyapunov function. And that's what we found here. It's a saddle point. So, because the covariant derivative has to be non-positive. If there's any increase in any direction, it'll become positive. Game over. So, okay. So that's how you can tell a function is not a Lyapunov function. So, now we come to the end. About the bet. So you did not hurt yourself. You blurted something out. So here's my amended deal.
No,
That-
that wasn't even
Yeah,
words.
that was me.
That wasn't even words.
Oh,
He was about to say something, and I was like,
Okay, at least it was.
Okay, you gave me permission to talk once. I did not use that.
that's true.
Okay.
It's true.
Yeah.
It's
It's
true.
true. He gave up his